Yesterday we defined simple harmonic motion for the first time as motion in which the restoring force, we'll talk a little bit more about the term restoring in a few minutes, but motion in which the restoring force, call it a force for now, motion in which the force is proportional to the displacement. So in other words, as something is stretched more or moves further away from where it started, the force is bigger. That's contrary to what we've learned thus far this year. It's different than what we've learned because so far this year, everything has been a constant force. You may have 14 forces acting on an object, but they're not changing. The force of friction acting on an object right here is the same as the force of friction acting on the object right here. The applied force is the same right here as it is right here. Gravity is the same here as it is right here. So the force hasn't been changing, but now we're talking about a force that varies with the position of the object. If the object is further away from where it started, the force is bigger. If it's closer to where it started, the force is smaller. So it's motion in which the force is proportional to or related to the displacement. Now, how is it that we kind of understand simple harmonic motion, our everyday recognition of simple harmonic motion? Well, whenever we see something going on out there, we're not necessarily constantly thinking or consciously thinking, oh, I wonder if the restoring force is proportional to the displacement. What we notice is whether or not the motion repeats itself. If the motion repeats itself, then we're going to say it's almost certainly simple harmonic motion. That's not the technical definition of simple harmonic motion, but it's the working definition that's going to help us to recognize when something is simple harmonic motion, motion that repeats itself. Now, we saw a couple of examples of that yesterday. The first one was the spring. When I stretch a spring, the more I stretch it, the bigger the force is required. Therefore, it's simple harmonic motion. If I let that spring go, then the motion of the spring is going to go back and forth, back and forth. The motion of the spring is going to repeat itself. An elastic, same deal. Although an elastic, you don't necessarily see it repeating itself quite so much, but it would. It's just that the disturbance dies out fairly quickly. So it doesn't repeat itself for very long before other forces kind of take that disturbance away. Another example that we saw yesterday was the pendulum. Right? When I swing the pendulum bob on the end of the string, it goes back and forth, motion that repeats itself. The restoring force is pretty much, in that case, proportional to the displacement. Again, a good example of simple harmonic motion. We learned a little bit about the pendulum specifically yesterday, including an equation that showed us which variables affect the period of a pendulum. Period, by the way, which is the time for one complete cycle, as opposed to frequency, which is the number of cycles per time, per second. The period of a pendulum specifically could be found by using the equation 2 pi square root L over G. That tells us that the period of a pendulum is not dependent upon how heavy the pendulum bob is. It's not dependent upon the initial angle that the pendulum is dropped at least to a certain amount. It's not dependent upon the angle that it's dropped at. It's dependent only on two things. One, gravity, which we can't control. And two, it's dependent upon the length of the string, which we can control. We saw how to rearrange this equation yesterday as well. Want to solve for L? Let's take the 2 pi over by dividing. And then let's square everything on both sides. We get T over 2 pi squared equals L over G. And then if we want to solve for L, let's take the G up by multiplying. So it becomes L is equal to G times T over 2 pi squared. And it looks a little bit ugly, but is what it is. We can go from that if we want to solve for the value of G. Go from that and divide L, or divide both sides really, by T over 2 pi squared. Bring it over to the other side. We get L over T over 2 pi squared. And this is what we get when we solve for G. Can't remember whether it was this class or the other class. I said when we're solving these problems, especially with this equation, the last one, like do it in steps. Right? Solve for 2 pi. Press equals. And then say T over 2 pi. Press equals. And then square that. Press equals. And then L over that. Press equals. So I say that, and then somebody, I think it was the other class, said, "I'm not getting the answer you're getting." And why aren't they getting the answer that I was getting? Because they didn't do it in the steps that I showed you, right? This is a tricky equation if you want to just try to use brackets in your calculator. It's doable if you're really good in your calculator, but my strong suggestion would be get this number, then get this number, then get this number, then get this number. All right, we had a few questions that we were working on yesterday on pendulums, and those questions were on page 379. Is there any issues with those questions on page 379? Questions 1, 2, or 3? We're all good with all three of them? Excellent. Love it when you guys nail something right off the top. It's good. All right. I'm going to assign a few more questions. I'm going to get you to work on those for a little while right now, and then we're going to do some new stuff after that on a little bit more simple harmonic motion. Questions that I want you to work on right now are on page 347, and I'd like you to work on questions 1 through 12 on 347. All right, I want to switch gears a little bit from the pendulum that we were talking about yesterday and that we reviewed here today. Go back to the spring and talk about the simple harmonic motion of that spring. We know that as we pull a spring back, we know that the force that's required to pull it back, and therefore the restoring force, right, I pull it back with a force to the right, okay, the spring pulls my hand back to the left. The restoring force, the force that pulls the spring back to where it started from, is proportional to the displacement. Bigger the displacement, the more it's stretched, the more the restoring force. Now, if I stretch that spring back further and it requires more force and pulls back with more force, then that must mean there's going to be more energy stored in that spring. I stretch an elastic, okay, there's energy stored in the spring. You guys know this, right? Take an elastic, a hairband, whatever, put it on the end of your finger, pull it back, and let it go, and it flies off. There's kinetic energy, right? Where did it come from? It came from elastic potential energy or spring potential energy. We talked about that a little bit in our dynamics unit. Okay, the more we pull it back, the more energy is stored in there. Elastic potential energy or spring potential energy is the energy that's stored in the elastic or the spring that's been stretched or compressed. I want to talk about that in a little bit more detail now than we did back in our dynamics unit. So let's define it first. Okay, the energy stored in a stretched or compressed spring or elastic or something similar. On May 31st, when we do our amusement park field trip, one of the assignments that you're going to complete is going to be based on the bumper cars. And one of the questions, that's a pretty qualitative assignment. Most of them involve a lot of numbers. That one doesn't. That assignment involves a lot of sentence answers, right? Write a couple sentences about something. One of the questions says something to the effect of, why do we want to use rubber bumpers on the bumper cars? And the answer that we want from that is not, oh, because if you had metal bumpers, it would hurt. Okay, why? Why would it hurt if you had metal bumpers? Why doesn't it hurt if you have rubber bumpers? Okay, in the end, the rubber acts as kind of a spring or an elastic, and the energy that the kinetic energy that the bumper car has as it's moving and collides gets absorbed by the rubber bumper as opposed to by you, the driver of that bumper car. So it's better to store the energy as elastic potential energy in the rubber bumper than it is to transfer the kinetic energy directly to you and have you have a really big jolt and get whiplash or something like that. So elastic potential energy, spring potential energy is the energy that's stored in a spring or elastic or something similar like a bumper car bumper. The more the spring or elastic or bumper is stretched or compressed, then the more potential energy that we have there. The more energy is stored in it. I think I told you guys the story back when we did our dynamics unit. I thought when I was a little kid, we used to make these guns with hockey sticks and clothespins. I think I told you about that. Remember that? The more we stretched the elastic, the faster the little spring from the clothespin would go, right? The faster it would go, the more kinetic energy it would have. Well, where did it come from? It came from potential energy. The more you stretched it, the more potential energy it has, and therefore the more ability it has to do work, the more kinetic energy that it will have down the road when I release it. So, what's the equation for elastic potential energy? Remember, gravitational potential energy was EP is equal to mgh. Elastic potential energy says EP is equal to 1/2 kx squared. There's a couple new variables in there for you. EP is potential energy. In this context, it's elastic or spring potential energy. When we talked about gravitational potential energy, we used the same symbol, but it was the energy stored due to a height above something as opposed to due to a stretched or compressed elastic or spring. But still stored energy, still potential energy. The two new terms here are K and X. I want to define X first. X would be the displacement of the spring or elastic. Now bear with me on that for a second here. It's the displacement of the spring. I'll say the spring, but when I say the spring, know that I mean the elastic, the bumper on the bumper car, or whatever it is that's being squished or stretched. It's how much it's squished or stretched, the displacement of the spring or elastic or whatever. It's going to be measured in meters. So I've got an elastic in my hand right now. I want to distinguish between two types of displacement. The displacement that we've talked about all this year, right? The displacement meaning change in position of an object, the movement of an object, versus the displacement delta D, right? That displacement versus this displacement that we're talking about now, X. Okay, when I stretch this elastic out, put it on the end of my finger and stretch it out like this and let it fly, okay? The amount of stretching of this elastic is the displacement X. The movement of the elastic across the room is displacement delta D. We're not talking about how far the elastic goes when I release it. We're talking about how much it's stretched or compressed when I pull it back. Does that make sense? Delta D is the displacement, the movement of the elastic. X is the amount that the elastic is stretched or compressed. That's what we care about here when we're measuring the elastic or the spring potential energy, the amount that it's compressed or stretched. Thank you. K is a completely new variable for you. It's what we call the spring constant. And the units for spring constant are newtons per meter, newtons over meters. And the spring constant is essentially a value, a measurement of how stiff a spring or an elastic is. The stiffer it is, the harder it is to stretch or compress, but the more potential energy that it can store when you do stretch it or compress it. You guys have all done this before, right? You take the spring out of the inside of a pen, you know, one of those little springs. They're pretty loose springs, right? They're not very stiff springs. They can't store a lot of potential energy. You can't put one of those springs underneath your car, drive over railroad tracks, and expect it to hold your car up, right? It doesn't store that much potential energy because the spring constant of that spring is so small. But if you take a much stiffer spring, put it in your car, which cars have, right? On both sides of the car, there's springs that are very, very stiff with a very, very high spring constant. It'll store a lot of potential energy and it'll have the ability to hold up your car. The stiffer the spring is, the more potential energy that it can store, the higher the value of the spring constant. All right? Now, sometimes you're going to be given the value of the spring constant, sometimes you're not. Sometimes you're going to need to find it. Well, here's how we're going to find it. Using a law, a new law, that we call Hooke's law. Hooke's law is really just a statement, a mathematical statement of the definition of simple harmonic motion. Hooke's law says the following. The force, actually let's just make it, let's not put the absolute value signs around it. The restoring force, the force that pulls a spring back to where it started, right? When I pulled that elastic back, that hair elastic back a minute ago, let it fly, yeah, I pulled it with a force of, let's say, 5 newtons. It pulled back with a force of 5 newtons. It wanted to go back to its natural position. That force that pulled it back to its natural position was the restoring force. The restoring force is equal to the spring constant times the displacement, but it's really a negative in front of it, because really if I pull it to the right, if the displacement is to the right, then the restoring force is to the left. If I pull it to the left, the restoring force is to the right. That's Hooke's law, which again is really just a statement, a mathematical statement of simple harmonic motion, because we define simple harmonic motion as motion in which the restoring force was proportional to the displacement. Bigger the displacement, bigger the restoring force. Now, how does this help us with this stuff? Well, if you want to find the spring constant, what will often happen is that you're given the force and the displacement, and you have to find the spring constant and then turn around and plug that back into here. Now, notice I've dropped a negative there. Well, remember that if I pull on an object, if I pull on an elastic or a spring with a force of 10 newtons, the restoring force would actually be negative 10. When I'm finding the spring constant, I'm typically not going to use the restoring force. I'm typically going to use the applied force. So it's not going to be a negative. Let's put a little subscript R beside that. And let's put a little subscript A beside that. The restoring force, the force that pulls the spring back to where it started, is negative kx. The force that I'm pulling with, the applied force, which is usually what I want to use to find the spring constant, is kx, which rearranges itself for k becomes F over x. It's really the same equation. The restoring force is a negative, the applied force doesn't. I'll tell you what, if on a test you get that mixed up a little bit and you put a negative where it's not supposed to be there, I'm probably going to overlook that. Okay, I want you to use the right equation, but if you make it negative when it should be positive or vice versa, again, we'll probably just pretend that didn't happen, right? I want you to understand it, but it's okay if you make a little mistake on that. It's not the end of the world. It's the same value of force. One's just the force that pulls it back in one direction. One's the force that I pull it with, exact same value, but in the opposite direction. So you may have to find the restoring force with this equation that's on your data sheet. You may have to find the elastic potential energy stored in a spring or elastic with this equation. You may need to find the spring constant in order to put into this equation, and then you're going to use a slightly modified version of this equation to find that spring constant, dropping the negative because you're dealing with applied force as opposed to restoring force. Okay? All right, let's take a look at example 301. Back to chapter 6 now. What were we doing yesterday? Chapter 7, we're regressing now. A spring is stretched to a position 35 centimeters from its equilibrium position. The equilibrium position, by the way, is its normal position. I got a spring. It's sitting on a desk. That's in its equilibrium, its natural, its normal position. When I stretch it, all of a sudden it's not in its equilibrium anymore. Anyways, in this case, we've got it stretched 35 centimeters beyond the position it would be in if it was sitting on the desk, not being touched, the equilibrium position. And at that point, the force on the spring is 10.5 newtons. That would be the applied force as opposed to the restoring force. What's the elastic potential energy? And if the spring is allowed to reduce, the stretch in the spring is allowed to reduce to 20 centimeters, what's the change in elastic potential energy? Okay, let's worry about A first here. Come to B in a minute here. We have a displacement in A of 0.350 meters. And we have an applied force of 10.5 newtons. We want to find the elastic potential energy. All right, to find the elastic potential energy, let's say EP is equal to 1/2 kx squared. All right, we know what x is, that's great, but we don't know what k is, so we got to find that. On your data sheet, you'll see an equation that says F is equal to negative kx. That's the restoring force equal to negative k times the displacement. If I change that to the applied force, then I would drop the negative. And it would just be kx, because the applied force is opposite to the restoring force. When I rearrange that, I get an equation that looks like this. 10.5 newtons over 0.350 meters. That gives me a spring constant of, I think it's 30, isn't it? 30 newtons per meter. That's where the units for spring constant come from, right? F over x, newtons per meter. So we're going to say 1/2 of 30 newtons per meter times 0.350 squared gives me, I'm not sure, but we could find it, 0.5 times 30 times 0.35 squared gives me 1.8375. And the units for that would be joules. We're going to round that to 3 digits, 1.84 joules. All right, what about question B now? If the stretch in the spring is allowed to reduce to 20 centimeters, what's the change in the elastic potential energy? Don't make this question harder than it has to be. The elastic potential energy was 1.8375 joules when the displacement was 35 centimeters. When I reduce the displacement to 20 centimeters, I don't have to change everything. I'm going to say EP is equal to 1/2 kx squared. I have to do that equation again, but I don't have to find the value of K again. I can keep it as 30 newtons per meter. But wait, we changed the value of the force. Sorry, we changed the value of the displacement, right? If we change the displacement, change the situation, isn't K going to change? It's the same spring. The value of the spring constant is still the same. How can it be the same if X is different? Because F is different as well. When I change the displacement, F and X are both different. So the spring constant of that spring ends up remaining the same. Once I found it, I've got it, 30 newtons per meter. Now, the only thing that changes here is the displacement. We're going to make it 0.20 meters instead of 0.35 meters. And when I do that one, what do I get? 0.5 times 30 times 0.2 squared gives me 0.6. Now, if I want to find the change in elastic potential energy, then I'm going to say 1.8375 joules minus 0.6 joules gives me, actually it should be the other way around, right? Final minus initial. 0.6 joules minus 1.8375 equals, is that going to be negative 1.24 joules? Is that okay? So when I allow this, here's a question for you. When I pull this spring 35 centimeters, when I stretch it 35 centimeters, it's got 1.84 joules. When I let it go, let's say I'm not just kind of reducing its stretching, but I actually let it go. Okay, so I stretch it this far, I let it go, I let it vibrate back and forth. At that moment, when it's only stretched 0.2 meters, and there will be a time when it's only stretched that far, right? Not because I was gradually letting it go back to 0.2 meters, but because when I let it go, it's going back and forth, back and forth. At some point, its compression will be 0.2 meters. Can anybody tell me what its kinetic energy would be at that point when it's stretched only 20 centimeters versus 35? What would its kinetic energy be there? I stretched it. I gave it 1.84 joules of potential energy. I let it go, and as it passes through 20 centimeter extension, what's its kinetic energy, Rosie? Sorry? Not 1.84, no. When it passes through its equilibrium, not stretched at all all of its potential would be converted to kinetic, and its kinetic energy would be 1.84. So its max potential is when it's fully stretched. Its max kinetic is when it's going through the equilibrium. But when it's still 20 centimeters that's extended, its kinetic energy would be 1.24. Why? Because when it's fully compressed or stretched, it has 1.84. When it's 20 centimeters extended, it has 0.6. So the rest of it must be in the form of kinetic energy, right? Which would be 1.24. Is that okay? That's a situation where potential energy is being converted to kinetic. And the less it becomes stretched, the closer it becomes to its natural position, its equilibrium position, the less potential we have, the more kinetic we have. All right, let's see what you can do with, oh my goodness, 5 practice problems. See what you can do with those ones, please.